here. All kinds of fun stuff. Let's see. All right, so now we're into section 14.12, which deals with fragments. Now, if you think about the mass spectra that we looked at before, let's just review. We had the parent ion, and of course, for bromobenzene, our parent is this first line here, and then we have the M+2 peak, which is 2 units higher. So then we have our base peak, which is here. But all these other peaks here, these are fragments, okay? Little fragments. Even the base peak is a fragment in this molecule. This would be considered a fragment. And so now what we're going to get into is analyzing fragments. Now you can imagine this is a very broad topic that can, take a long time to study, but we're going to look at the most important fragments that you would need to know for Chemistry 3101, and these would probably be the same ones, or a lot of the same ones you need to know for the lab as well. So let's go back to our pentane molecule. If you remember, our pentane molecule has a formula of C5H12. So we have a total of 60 plus 12, so that gives us a parent ion, which would be equal to 72. All right, 72. So what are the possibilities for fragments? Well, the thing is that we have 1, 2, 3, 4 sigma bonds between carbon atoms in our pentane molecule, and any one of those bonds technically could fragment. Let's just imagine that this bond here was to fragment, the one I have the little blue mark on. Well, let's say you lost a methyl radical, okay? You lost a methyl radical. Well, what's the mass of a methyl radical? It happens to be 15, okay? This has a mass of 15, okay? So we'll put here 15. I'm not going to put mass over charge because it doesn't have a mass, or sorry, it doesn't have a charge. It just has a mass of 15. So if you take 72 and you subtract 15, you would see this butyl carbocation, right? And what's the mass of that going to be? Well, that would mean that in the mass spectrum, you're going to see something with a mass over charge of 57. So something with a mass over charge of 57. And when you see that peak at a mass over charge of 57, you'd say, well, I lost 15, so I lost the methyl radical. Okay, let's go to the next one. If we were to break the next sigma bond, I'll use my red pen here, okay, you would lose an ethyl radical. Well, what's the mass of an ethyl radical? You got 2 times 12 for the 2 carbons, so that gives you 24 plus 5, which gives you 29. So this has a mass of 29. Now, if you take 72 and you subtract 29 from it, what does it mean? It means you're going to see something with a mass over charge, a mass over charge equal to 43. So what you see here, this propyl cation has a mass over charge of 43. So you're going to see the peak at a mass over charge of 43. But what that means is that you've lost 29. You've lost an ethyl radical. You can see where I'm going with this. If you were to cleave the next bond, if you were to fragment here, right, if you were to lose a propyl group, well, a propyl group, okay, that has a mass of 43. So this has a mass of 43. If you take 72 and you subtract 43, you get a mass over charge equal to 29. So you would see this fragment, this ethyl carbocation in the mass spectrum. And then for the last one, if you lost the butyl, well, that has a mass of 57. And so you would see something, excuse me, that has a mass over charge equal to 15 for the methyl carbocation. Give me a thumbs up if you're with me on the rationale of how this thing is breaking apart, right? And just where the masses come from, okay? Now remember that all of these fragments are not going to have the same abundance, okay? Some of them are going to be more abundant than others. For example, you're going to see more of any of these than you would of this one here. That's based on the stability of a carbocation, because when we have a carbocation, you should remember that carbocation stability. Let me just scribble it down here. When we're talking about carbocation stability, right? It goes tertiary carbocation, which is more stable than secondary, which is more stable than primary, which is more stable than a methyl carbocation. So somebody says, how do you lose one group over another when we're bombarding the molecule with electrons? Well, again, you make one radical cation, right? You make one radical cation here, and that can fragment a number of ways, right? We're not talking about one molecule fragmenting, right? We're talking about moles of molecules that can undergo fragmentation. So when is it going to, why would it fragment preferentially to lose the propyl group rather than a butyl group? Well, the reason why is because the carbocation that you get when you lose the propyl group, okay, where's my black pen? This one here, this is a primary carbocation because this carbon is attached to one carbon, but this one here gives you a methyl carbocation, and a methyl carbocation is less stable. So it's preferentially going to give you a primary carbocation over a methyl carbocation. That same question is answered on this slide as well. Let's say you have this molecule here, okay? Let's say you make this radical cation here. There's all kinds of places this could fragment, right, Sarah? It could fragment here. I mean, if it fragmented here or here, that would be identical. It could fragment here, it could fragment here, and it could fragment here. So you have all these different possibilities. But what they're telling you is that even though you have all these possibilities for fragmentation, the one that's going to occur the most is the one that I have in red. Okay, why would that one be the greatest fragment you're going to lose? Is because with this case, you'd end up with a tertiary carbocation, right? So a tertiary carbocation is going to be more stable, right? If you go back here, tertiary is more stable than secondary, primary, et cetera, et cetera. All right. Does that make some sense now? Cha? All right. Hopefully that makes some sense. Okay. So the more stable the carbocation, the greater propensity there's going to be to form that carbocation. All right. Well, let's move on from there. Okay. So let me just give you a heads up. I've taught this class plenty of times. So let me just tell you something before I get into the nuts and bolts. This slide, so I don't know what number this is, slide 57, slide 58. Okay, so these two slides, 57 and 58. 57 and 58. These ones cover specific rules of fragmentation that you need to know, okay? So the first slide, 57, deals completely with alcohols, and then slide 58 deals with amines and then aldehydes and ketones, okay? So the first page, or first slide, 57, deals with alcohols. Alcohols take up a whole slide to themselves because there's two different ways that alcohols can fragment, okay? And you just need to memorize these. The first one is alpha fragmentation, okay? So if you're like, oh, darn, there's those single-headed arrows again, don't worry about those. Let's say we take an alcohol like this here, okay? So remember, oxygen has two lone pairs and two bonds when it has no charge. You hit it with a high-energy beam of electrons. So beam of electrons, okay? You knock one electron off, so you make a radical. Now, what happens is the carbon that is attached to the oxygen, we call this the alpha carbon, okay? So this is called the alpha carbon, and we just label it with the letter or with the Greek letter A, or alpha, okay? So you don't have to be able to draw these arrows whatsoever because that's not covered till chapter 10. What you need to know is this, okay? Watch very carefully. Is that once you form the radical cation, you get what's called alpha cleavage. And all it means is that the bond can break between the alpha carbon and the next R group. So it could break here where I have this blue line drawn. And what they're showing here on the slide is they're showing this bond being broken between the alpha carbon, and then this would be a beta carbon here. But it could break on either side. They just happen to be showing this one that I have in the circle, okay? So we call that alpha cleavage. And if you're wondering, well, which side is it going to break on? It doesn't matter. That's neither here. It could break on either side is the idea, okay? We call that alpha cleavage, and we'll look at an example of it. If you're wondering, well, why does it happen? You know, like this goes back to Sarah's question, why does it happen? It's because when it happens after the alpha cleavage, you end up with a cation that's resonance stabilized. Okay, you end up with a resonance stabilized cation. You don't have to draw it. I'm not going to ask you to draw it on a quiz or anything like that, but that's why alpha cleavage occurs. The second thing is usually easier for students to remember. If you think about every single time I showed you a fragment today, okay, in case you didn't notice, 43, Here you lost 57, 29, 15. Did you notice that everything that we lost was an odd number? Everything is an odd number. So here's an exception to that. When you have an alcohol can also lose water. Well, what's the mass of water? Water has a mass that's equal to, so mass is equal to 18 grams per mole, or 18 AMU, right? 16 for the one oxygen, and then 2 for the 2 hydrogens. So we get a mass of 18. And so it's one of the few times that we see is this thing frozen? It's one of the few times that we see an even, no, it's not. One of the few times we see an even mass being lost. So if you see a loss of 18, it's a dead giveaway that you've got an alcohol. All right, you don't have to draw a mechanism of it or anything like that. So that covers alcohols, okay? So check. The next slide, slide 57, has 2 different concepts on it, okay? So we squeeze a lot of information in here. The first half deals with amines, and the second part deals with carbonyls. And let me go over the amines with you first, okay? Amines can undergo alpha cleavage the exact same way an alcohol could. You take the amine, you smack it with electrons, you make a radical cation. Then it can undergo alpha cleavage. What's the alpha carbon? The alpha carbon is the one attached directly to the nitrogen. So it could cleave on this side of the alpha carbon, or it could cleave on this side of the alpha carbon. You do not have to draw the mechanism. On this particular slide, they're showing the bond being broken here. Okay, but it could break on either side. So that's alpha cleavage. Again, why does it happen? It happens because we end up with a resonance stabilized cation. Okay, so that's alpha cleavage. Alpha cleavage is a thing for both amines and alcohols. Let's go over the last one. Okay, first I'm going to address what is a carbonyl. I've taught you that carbonyl means a carbon with a double bond to oxygen like this. But when we say carbonyls, okay, in organic chemistry, and this is where students are like, oh, good gravy. Okay, you go from a carbon. So this is a carbonyl. A carbonyl, and a carbonyl is found in esters, carboxylic acids, aldehydes, ketones, acid chlorides, etc., etc. When we say carbonyls, it means aldehydes and ketones specifically. Okay, don't get angry at me. I'm just the messenger. Okay, so if you have an aldehyde or a ketone, they can undergo a rearrangement called the McLafferty rearrangement. All right, and you're probably going, what is all this here? Okay, again, you don't have to memorize those arrows or anything. All you have to know is what a McLafferty rearrangement is. Okay, you ready? So here's what a McLafferty rearrangement is. If you have an aldehyde or a ketone, okay, and whenever you have an aldehyde or a ketone, I'll just draw a carbonyl and put 1, 2, 3, 4, something like this. Does anybody know any of the Greek alphabet? Right? Hopefully you know alpha, and then beta, and then gamma, and then the next one will be delta. Okay, so here's the rule. If you have an aldehyde or a ketone and it has a 1 hydrogen on the gamma carbon, at least 1 hydrogen on the gamma carbon. So this gamma carbon has 2 hydrogens, but so it's got at least 1, right? It can undergo what's called the McLafferty rearrangement. And if you're like, well, how am I going to know if I can't draw all those arrows? The reason you're going to know is because the mass that's lost, okay, so this is the mass that's lost here, has an even mass. So we'll put here mass lost is even, okay? So this molecule here has an even mass. And so if you have an even loss, or sorry, the loss of a fragment that has an even mass and it's not 18, then it might be an aldehyde or a ketone, and you might have had a McLafferty rearrangement occurring. And if you're like, well, what's the mass? And again, an even mass that's not 18, okay? The exact mass isn't really all that important. If we were to calculate the mass of this, this fragment here, we have C6. So we have 6 times 12, which gives us 72. And then we have a total of 1, 2, 3, 4, 5, 6, 7. So we have 12 hydrogens. So that gives us a mass over charge of 84. So we have mass over charge of 80. Sorry, I put mass over charge when it doesn't have a charge. My mistake. Mass is equal to 84. Are you with me on that idea, McLafferty? Again, you don't have to draw the curved arrows. The idea is if you have a gamma carbon that has at least 1 hydrogen on it, you can have a McLafferty rearrangement. That's it. All right. Every once in a while, a student will raise their hand in class, and it's a great question. They'll say, Mr. Dion, do you have all this information summarized in a table somewhere? Great question. And the answer is yes. These are the fragments that you need to know for Chemistry 3101. 3101. They're the most common fragments in mass spec. This is what you need to know for Chem 3101. Now, I'm just going to say, I think that a few of you, at least, are taking the lab currently with Mr. Geiger. If you're in Mr. Geiger's lab, he will probably go into more detail on mass spec. And so he will probably have some other fragments that you're going to need to know. And so that's up to him, okay? But just to put that bug in your ear for this class, we look at a little bit less fragments, and in the lab, he throws a couple of extra ones at you. Cool? So 15 is loss of a methyl. 29 is an ethyl. So a methyl radical is just this, CH3 radical. An ethyl is just this, CH3, CH2 radical. Propyl is CH3, CH2, CH2 radical. I'm sure you can all draw the butyl radical, which is this. Loss of water is obviously H2O, and then something with an even mass. That's when you have a ketone or aldehyde. So I'll just draw 1, 2, 3. So we have first is our alpha carbon, then our beta carbon, then our gamma carbon. If the gamma carbon has at least one hydrogen on it, it can undergo a McLafferty rearrangement. All right. And then you lose an even mass. It's the only time we see an even mass except for the water loss, which is 18. All right. So that's a lot of talking today. Let's take a look at a problem before we look at the last section here. This is question 14.25 from our textbook. It says identify two peaks that are expected to appear in the mass spec of 3-pentanol. Identify the fragments associated with each peak. Okay, so look, I am not going to ask you to identify the fragments on a quiz, okay? I won't ask you to identify what the pieces are. And I'm also not going to expect you to be able to name 3-pentanol or draw the structure because we haven't covered alcohol nomenclature. I would give you the structure. So this is 3-pentanol here. All right, and we could go ahead and calculate the molar mass of this compound. So it's C5H12O. Did anybody calculate the molecular or the molar mass of 3-pentanol? Anybody? So we get 60 plus 12 plus 16. So exactly, we get 88 for this one, right? Because there's 12 hydrogen, so it would be 88. So that means we would have our parent ion would be at 88. Now, what are the two possibilities here? Okay, what are the two possibilities? Well, if we go back here in our notes, we said that when we have an alcohol, it can undergo alpha cleavage, or it can undergo a loss of water. So I'm not going to draw the mechanisms because I'm not going to ask you to draw those mechanisms on a quiz. But let's just do loss of water. So loss of H2O. That means we're going to get a mass overcharge, mass overcharge at M plus minus 18, okay, or the molecular ion minus 18. So if we take 88 and we subtract 18, that means we should have something with a mass overcharge equal to 70. So that would be our first fragment, okay, is from loss of H2O. The other possibility is going to be an alpha fragmentation, an alpha cleavage. So for an alpha cleavage, I'll do this one in, now maybe I'll just redraw the molecule. So if I redraw the molecule like this, okay, and you can practice drawing your radical cation, right? You have all of your electrons here, you lose one, you end up with a radical cation, okay? And this has a mass overcharge that's equal to 88, right? Because you lost that one electron, so now it's going to charge, okay? And now this could undergo an alpha cleavage. So we'll put here alpha cleavage. You don't have to draw the arrows. Now you notice that this molecule is symmetrical, so whether we cleave here, right, because this is our alpha carbon, or if we cleave here, we end up with the exact same thing, okay? So what are we going to lose is we're going to lose this portion here. Let me use my red pen. We're going to lose this portion here. So what we're going to lose is going to have a mass of 29. So we'll put here loss of 29. So it's going to be m minus 29 is what we're going to have. So we have m minus 29. And this is an ethyl radical. So ethyl, just scribble it here, ethyl radical. There we go. And so what are we going to end up with if we take 88 and we subtract 29 from it? So we take 88, subtract 29. I want to make sure I don't do my mental math incorrectly. So we get a mass over charge equal to 59. So that means we're also going to see a mass over charge of 59. And that is going to come from alpha cleavage. Where's my, there we go, alpha cleavage. All right, those are the two possibilities. And there you have it. Now, in the textbook, it might draw the fragments, but again, that's assuming that you did the textbook in sequence, going from chapter 1, 2, 3, 4, 5, 6, 7, all the way up to 14. Since we skipped that, I'm not going to ask you to draw the fragments. All right, there you go. So those are the two possibilities for the fragmentation of 3-pentanol. All right, so we're going to skip, I'll write it down here. We are going to skip section 14.13, 14.14, and 14.15. I'll leave that as an FYI. If you want to read that, it's definitely interesting, but it's nothing that we cover, and it's nothing that's covered on the final exam. So the very last section deals with degrees of unsaturation. We call this a U, okay? We call this a U, or sometimes we call it an HDI, a hydrogen deficiency index. So it says here that mass spec is usually used to determine the molecular formula of a compound. Like I said, the IR can help us determine functional groups. And you probably remember that if we have an alkane or a saturated hydrocarbon, it has a formula of CnH2n plus 2. Right? So let's say you had something like, we'll put here, example, if you have decane, it would be C10H2n plus 2. So you take 2 times 10 plus 2. So that would give you C10H22. All right, nothing really new under the sun there. There we go. All right, so what's a degree of unsaturation? A degree of unsaturation is where we start to lose hydrogen. So for every degree of unsaturation, we lose 2 hydrogens. The possibilities for a degree of unsaturation are either a pi bond or a ring. Students always remember pi bonds, but sometimes they forget a ring will do the same thing. Okay, so let me show you an example. If you have an alkane, remember that the generic formula is CnH2n plus 2. Well, if you form a double bond, that means you've lost 2 hydrogens, right? We go from 12 to 10. And so our formula now is going to be, for an alkene, would be CnH2n. And that you see for an alkyne, we lose 4 hydrogens. So our formula is CnH2n minus 2 is what we get there. And so the compounds where you lose hydrogens, these are unsaturated compounds. Now, if you're wondering about a ring, what if we had a 5-membered ring like this? Okay, we have 5 carbons. And so what's our formula going to be? It's going to be C5H10. So if we have a cycloalkane, we'll put here cycloalkane. Let me make sure that's an A so you don't get confused. A cycloalkane has a formula of CnH2n, just like an alkene does. It's the same thing. And then we have an alkyne, which is CnH2n minus 2, alkyne. There we go. And then we have alkane up here. All right, so a ring or a pi bond counts as a degree of unsaturation. So let's say you have a molecule that's C4H6. That follows the formula CnH2n minus 2. So that tells you that it has an HDI, okay, or a U of 1. So we say HDI stands for hydrogen deficiency index, and then U stands for units of unsaturation. We'll put here or U, and then we say it's 2. So what are the possibilities? Well, there's 4 possibilities. You could either have 2 double bonds, you could have a triple bond, you could have 2 rings, or you could have a ring and a double bond. And if you're looking at all these compounds and going, good gravy, you know, which one is it going to be? Well, to figure it out, you'd have to probably use IR and then maybe NMR, which we're going to look at in chapter 15. But at least it gives you an idea of what the molecule could be. It gives you some possibilities. So when we're calculating an HDI of an organic compound, we look at haloalkanes, we look at alcohols, we look at alkenes, alkynes, all these different kinds of molecules. So how do you calculate the HDI for something that's got a halogen in it? Well, if you have a halogen in your molecule, it actually doesn't affect unsaturation any way at all. A halogen is just like a hydrogen because all the halogens, chlorine, fluorine, bromine, and iodine, in organic chemistry, they only ever form one bond. Okay, no exceptions to that in our class. So we treat it just like it was a hydrogen atom, right? A hydrogen just has one bond, so it doesn't affect anything. Same thing with an oxygen. An oxygen has no effect at all. It doesn't change anything whatsoever. So halogens, let me highlight it. Halogens and oxygens don't do anything to the HDI whatsoever. If you have a nitrogen, that's where it gets interesting, okay? So nitrogen increases the number of hydrogens by 1, okay? So let's say you have ethane, it's C2H6. Well, if you have a nitrogen in there, you have to add a hydrogen. So we have C2H1, 2, 3, 4, 5, 6, 7, N. All right, so you add 1. And I'll just level with you right now that what my students usually use is this formula. The formula for the HDI or U is this here. 1/2 times the number of carbons, 1/2 times 2 times the number of carbons plus 2 plus the number of nitrogens, subtract the number of hydrogens, subtract the number of halogens, and that gives you the answer just like that. I'll be honest with you, you've got to memorize this formula. I'm not going to give you this formula, so we'll put here memorize. You've got to know the formula. So with that in mind, let's try a practice problem here, calculating HDI. So let's try A. Could anybody calculate the HDI for this one? We're going to say HDI is equal to 1/2, 2 times the number of carbons, so that's 2 times 6. And then we have plus 2 plus the number of nitrogens. There's 0 of those. Subtract the number of hydrogens, so that's 10. Subtract the number of halogens. There's none of those. What do we get? We get 12 plus 2, which is 14, minus 10, which is 4. So that means we have an HDI of, anybody? What would my HDI be for this compound? If you have to bust out your calculator, just do it. Like I said, you can use a calculator on this quiz. Anybody get the answer to this one? Pablo, are you there? An HDI equal to 2 for this one. Anybody there? Okay, all right, one person. Thanks, Kiana. All right, thanks, Sean. Awesome. What about this one here? HDI equals, we're going to solve all of these. HDI, it's just a practice on using the formula. That's all it is. Okay, so we have HDI equals, and then the last one, HDI equals. Did anybody get B? Right, we treat an oxygen like it's nothing, right? Oxygen doesn't affect anything whatsoever. So for this one, we have 1/2, 2 times the number of carbons, which is 5, plus 2. Then we add the number of nitrogens, there's 0. Oops. Then we subtract the number of hydrogens, there are 10. We subtract the number of halogens. So we get 10 plus 2, which is 12, minus 10, which gives you 2 times 1/2. So we have an HDI equal to 1. All right, for the third one, we get an HDI equal to 2. In the last two, we get 1. So we get 1 here And we get 1 there. All right. And that covers all of chapter 14. The entire thing, the whole kit and caboodle is done.